All right, I'm here with Chiara Marletto. Chiara, thanks for joining me.
Yeah, thanks for inviting me.
So thermodynamics is a branch of physics concerned with heat and work and entropy and related concepts. And it's been formulated a few different ways throughout history. And using constructor theory, you've improved upon the so-called axiomatic formulation of thermodynamics. So before we get into the constructor theoretic version of thermodynamics, I wonder if you could briefly outline the axiomatic formulation.
Yes, so I think this requires a detour on, in general, on thermodynamics and also this other branch of physics, which is called statistical mechanics. And there is a bit of history to be made in the sense that so the first idea of thermodynamics, was proposed round about the age of the Industrial Revolution, and during those times, people were concerned with the efficiency of heat engines that can transform a kind of energy which is useful energy capable of doing work into other kinds of energy, and vice versa. And at that point, I think it became clear that there were two kinds of different types of energies. One, exactly as I said, is work, which is usable for doing something useful, some useful kind of motion. And then there is heat, which is a form of energy that is not useful. So it's kind of disordered energy, if you like. Some way of talking about it in a popular way could be using this concept of disorder, which is not so accurate, but I think it's good to give a kind of first impression. The point is that when energy is converted into heat during a certain physical process, for example, when you brake with say your bike, the heat that is produced is not useful anymore to perform work. So part of the mechanical energy that you put into pushing your bike ahead gets lost once you perform the act of braking. And there is a law that kind of describes how these different kinds of energies, work and heat, get transformed into one another. And this law is, well, actually there are two laws. One is the first law of thermodynamics, and the other one is called the second law of thermodynamics. So the first law of thermodynamics is somewhat about the fact that no matter what you do with heat and work, you can't create energy out of no energy. So it's about the conservation of the overall energy in your system. And the second law is about the fact that once you convert work into heat, it's very hard to convert it back into useful work. In fact, it's impossible. And now the problem with this law, as I formulated it now, is that it's very, the concept of it's impossible to revert heat back into work. It's a very vague concept, and there are several inequivalent formulations of the second law that amount more or less to the same thing as far as heat engines are concerned, but they mean very different things as far as physics is concerned. So here is where the axiomatic approach to thermodynamics comes, because initially, as I said, when people like Kelvin, Clausius, Carnot, and so on were talking about the second law in terms of heat and work, so the concern was really about how can we have laws that tell us about the efficiency of these heat engines? So in that sense, the concern wasn't very much about fundamental physics. But then when it became clear that in the second law, there was an idea of irreversibility, then lots of physicists got very intrigued by this, because of course we know that the other kind of laws that we use to describe the universe, which are dynamical laws, are time reversal symmetric. I think Maria Violaris must have talked about it in another podcast. So the laws are the same, let's say, if you run them forward or backwards. So the idea of an irreversibility, which is what the second law requires, it's really at odds with the laws that describe the microscopic particles that are the constituents of the heat engines. And so the question is, how do we fit this idea of irreversibility, which seems to apply at the level of heat and work, with the fact that the things that can perform work on something or that can get heated up and so on are ultimately made of elementary particles which are obeying reversible laws. So that's a kind of issue. And then there are different ways of going about trying to solve that issue. And statistical mechanics was initiated by people like Boltzmann and then Gibbs and so on, is one way of reconciling this irreversibility that seems to appear at the macroscopic level with the presence of these reversible trajectories of microscopic constituents. And that way is useful because it kind of says to us that there is a regime, which is that of macroscopic physics, where the irreversibility can crop up, but actually fundamentally we have reversibility for these trajectories. But there's also a different approach to the second law, which is the one of just trying to formulate the law in more fundamental terms, where instead of trying to derive the irreversibility out of the reversibility, making some assumptions, some additional assumptions, you try to formulate the second law in an exact way. So in a way that is compatible with time reversed symmetric laws. So therefore it doesn't use approximations, and it's not necessarily dependent on the scale of the object that you're considering. And the axiomatic thermodynamics is trying to do this. And I think, so Chiara Theodori was the mathematician who first introduced this idea, and then there was, other people also, of course, tried to formulate the second law in similar ways. Of course, there's Planck there. More recently, I think Lieb and Igvansson worked on the same set of ideas. And the gist of the idea is very simple. So instead of trying to, as I said, derive the second law from these microscopic dynamics, which is what statistical mechanics does, in the axiomatic take, you state the law as following from a set of axioms or assumptions about the physical world. And these axioms you could call, I prefer to call them principles because they are laws about physics. And then you try to explain why this second law formulated in this way is actually ultimately compatible with the description of microscopic particles that is completely reversible. And the second law in this axiomatic approach takes the form of a very simple statement in a sense. So it says that certain tasks are possible, so they can be performed in one direction to arbitrarily high accuracy. But the inverse tasks, so, if you're trying, let's try to be concrete. So let's think of an example. Task could be cooling or actually heating up some volume of water from one temperature to another. This is a classic example. So the axiomatic second law says that a task of this kind is possible with side effects that only involve what thermodynamics is called mechanical means, and I'll explain in a second what they are. But if you try to do the reverse, so if you try to cool the water from a temperature to another, you can't perform the task to the same accuracy with just these mechanical means. So you need more other kinds of side effects to perform this task the other way around. And mechanical means are epitomized by this kind of system where you're lowering or raising a weight in a gravitational field. And the so the reason why they're called mechanical means is that they only involve systems that don't dissipate. So they work like a perfect spring or a flywheel, systems that don't have any source of dissipation. And so the statement of the second law in this axiomatic way is very promising because it's nicely self-contained and doesn't necessarily require the second law to be derived from fundamental dynamics, but at the same time has a gap. And here is about the point where I'm going to stop explaining. The gap is that the law as formulated, let's say, by Chiara Theodori and co, doesn't say what mechanical means are. So it just says there are tasks that are possible in one direction with just the aid of mechanical means. And if I'm trying to use mechanical means to perform the opposite task, the reverse task, that's impossible. But it's not said exactly what these mechanical means are. So the usual thing, as I said, is just to say, oh, mechanical means are anything that is equivalent to raising or lowering a weight in a gravitational field. But this is not very fundamental and it's very ad hoc. And I think for the purpose of classical thermodynamics, this was perfectly fine and very powerful, in fact. But the issue that I have from the point of view of fundamental physics is, if one wants the second law of thermodynamics to be as general as, let's say, other principles of physics, like principle of locality or the conservation of energy or other principles of that kind, you need to make this law free of ad hoc assumptions, and you need to make it scale independent. So in a way that doesn't just apply to macroscopic objects, such as weight being raised in a gravitational field, but it can apply to any kind of physical object. And currently, that is the problem that I think my work on constructor theory is trying to address. And there are also other attempts to bridge this gap between, as I said, a scale independent formulation of the second law and one that is scale dependent. But so the axiomatic approach provides a way to address this issue, but somehow doesn't quite do it. And I think that's where the work with constructor theory comes in.
Yeah, so this scale independence of the constructor theory formulation of thermodynamics strikes me as very important, in that traditional formulations of thermodynamics, and tell me if I'm mistaken, were never able to provide exact expressions of the laws or where exactly they would break down, given that they were scale dependent. Is that right?
Yes, that's correct. So I think so if you talk to a physicist, I think you will find more or less, the physicists are divided into, broadly speaking, two camps. Of course, many more, in fact, because there's always space for further, of course, subtleties. But let's say, broadly speaking, there's a camp of physicists who think that the second law is not fundamental. What do we mean by that? We mean a law that is approximate and only really holds for certain very specific situations that involve macroscopic objects. And we don't have to specify really the scale of these objects, but we can say that they have to be sufficiently large with respect to a certain property. Now, what sufficiently large means is never actually said specifically, but it's fair enough because, as I said, this kind of take on the second law really sees this as a thing that's only relevant where you have sufficiently big aggregates of atoms in certain regimes. And when you are out of those regimes, the law doesn't quite make sense. So if you have like a single particle, single atom interacting with another particle, such as a photon, it doesn't really make sense to think of the second law doing anything there, because all you have is just the dynamical laws that describe the atom and the photon, and those are reversible, and therefore there's no second law. This is the camp where where, I mean, I think that they would be content with the second law being just scale dependent as it is now. Whereas the other camp to which I belong is more dissatisfied with this idea that we have, we've got, say, principles like the principle of locality, as I said, the fact that there's no action at a distance. And this really holds at any scale. So, it's true for our scale. If I'm trying to communicate with you through a medium, there has to be a certain finite time before the degrees of freedom in your brain get changed by what I'm saying, because there is, a certain necessary delay due to the finiteness of the speed of light and so on. And it's true at the scale of single atoms, even lower scales and so on. But in our case, in the case of the second law, this is not true. So, the principle isn't quite, although it's a very powerful principle, it just stops being meaningful in certain situations. For example, when you don't have a well-defined temperature, or where you have very, very few particles, and so on. And the attempt, so that the stuff that Constructor Theory is trying to do now is to bridge this gap and formulate a law, the second law, in the same way, let's say, as principles of information theory are formulated. Of course, that doesn't mean that we would invalidate the reversibility of dynamical laws. What it means is that there is a principle that holds irrespective of the scale, and what you show is that it is, after all, compatible with the fact that time reversal symmetric laws are out there. So it's a bit subtle in a sense, because the fact that there is irreversibility in a certain sense doesn't necessarily mean that the dynamical laws have to be irreversible as well. You can show compatibility of an irreversible behavior with the reversible dynamical laws, just assuming that there are different levels of explanation, and the level of explanation where you have irreversibility, which is the one of the second law, is disjoint from the one where you are observing reversibility, which is that of the particles obeying certain dynamical laws that are reversible. And the way, the new element in the constructor theory approach is that the key to irreversibility is different from the one, let's say, that's used by statistical mechanics or other approaches. And it pushes this idea of the axiomatic thermodynamics one step further, because it really grounds this idea of mechanical means into physical properties of systems, specifically counterfactual properties, and specifically information theoretic properties. So that's kind of the way we try to get out of this problem in constructor theory.
Right, and you mentioned the compatibility of irreversibility at a higher level with underlying reversible dynamics. So I wonder if you can connect that to an idea that you introduced in your paper, which is the difference between a process being permitted and a task being possible, and what that means for thermodynamics.
Yes, this is a very nice question. And I think you rightly point out the fact that the irreversibility is, as you say, not at the level of dynamics or trajectories, but it's at the level of tasks being possible or impossible. So, usually in a dynamical law, what you do is that so a dynamical law could be seen as a set of constraints on what trajectories in space-time, if you want to be super general, are allowed. And the fact that these laws are time reversal symmetric just means that if you allow one trajectory, then you have to allow the time reversal of that trajectory. So, if you got, in simplified terms, on these trajectories as a particle moving from A to B, then you will have to allow in your theory also the trajectory where the particle moves from B to A. There are lots of subtleties about how to define time reversal in fundamental physics, but this is a separate concept. So at the moment, I'm just going with a very basic concept of time reversal symmetry. And on the other hand, so this kind of reversibility is really all about trajectories and their being allowed, and what kind of trajectories are allowed. Once you say that one is allowed, you have to say also that the time reversal is also allowed. But the irreversibility in constructor theory is a different kind because it's about tasks. So again, this requires a bit of step back. So when a task is possible, that means that, so a task is just a transformation of a physical system from some state A to another state B. So in that sense, it looks a bit like a trajectory, but actually it's not, because when we say that the task is possible, we don't mean that the trajectory for the object to go from A to B is allowed. What we mean is that the task of going from A to B can be performed with arbitrarily high accuracy by coupling the system in question with an environment, and having this environment perform the task once, and then crucially retaining its ability to perform the transformation again. So, so the fact that the task is possible really means that you can bring it about with as many resources of the environment as you like, as permitted, in fact, by your physics, with the requirement that when these resources are used in order to perform the task, the ability that they have to perform the task is maintained, so they kind of work in a cycle. An example of a possible task is, say, you know, if you want to perform a NOT gate on a state, on a bit, for example, you want to go from 0 to 1 or 1 to 0. So that task is possible, we say, because you can build more and more sophisticated computers that perform that task to arbitrarily high accuracy. And the task is impossible when there is something that intervenes and stops, let's say, this environment from being capable of performing the task to arbitrarily high accuracy and retaining the ability of causing it again. So obviously an example is the conservation of energy. So when we say that energy is conserved, and we consider the task of going from zero energy to non-zero energy, that task is impossible, because if you try to do that with an environment that stays unchanged, you would violate the conservation of energy, in the sense that you would be suddenly creating some energy out of zero energy and have no side effects on the environment. So that's impossible. The environment has to change, specifically has to provide some energy to allow for this task to be performed. And so the energy can't be unchanged in its ability to cause a transformation again, because its energy will be lowered and lowered again and so on. And then at some point it will run out of steam and it will not be able to perform the task again. Now so therefore, as I said, the fact that the task is possible doesn't mean that the trajectory of, you know, going from state A to state B is allowed. It means that it's the process that performs the task to arbitrarily high accuracy is permitted. And now the observation here, which is crucial, is that while under time reversal symmetric laws, the fact that the task is possible in one direction, but the fact that the trajectory is allowed in one direction but not in the other, is not permitted, because, you know, if you have, as I said, the trajectory that goes from A to B, you have got to have the inverse trajectory also that goes from B to A. It's still logically possible that under these time reversal symmetric laws, you have some task which is possible in one direction, so you can perform it to arbitrarily high accuracy. For example, as I said, heating up some volume of water with mechanical means only. But if you try to perform the reverse task with those means only, you can't, and the task is impossible. And that's because if you try to just simply reverse the dynamical laws that perform the task in one direction, you will not get a process which performs the opposite task, the reverse task, to the same arbitrarily high accuracy. So the fact that the laws are time reverse symmetric doesn't help you in having the possibility of a task both in its forward direction and in its backward direction. So it's still kind of fine if you have time reversal symmetry at the level of the dynamics of the elementary constituents. But then if you consider the, the level of tasks being performed and the fact that you have possible tasks in one direction, but impossible tasks in the other is still a perfectly fine feature. And this is how you can reconcile irreversibility at the level of the second law with time reversal symmetry.
Yeah, I thought that idea was very cool. And it was before you even worked on the laws in your paper. So I thought that was very interesting. So speaking of the laws of thermodynamics themselves, right before we get to that, I want to talk about a couple more introductory concepts, which are work media and heat media that you use in your Constructor Theory of Thermodynamics paper. So I wonder if you could explain what these are and if you could maybe give an example of each.
Yes, so so as I said, the key to solving, so let me just clarify one thing before we start discussing this, that the idea that I just said that, a task could be possible in one direction, but impossible in the other, and yet the laws could be time reversal symmetric, is in a sense an idea that was already discussed widely in the foundations of thermodynamics in some form, not necessarily in this constructor theoretic form where possible and impossible are precisely defined. But I think, let's say Planck, for example, already had this idea of possibility and impossibility being still compatible with time reversal symmetry. So I think what constructor theory helps you with here is, one, that it provides a more general and also more rigorous definition of what possible means in the form that I just discussed in the previous question. And two, it, in the specific case of the law of thermodynamics, when you say that the second law could be formulated, let's say, as saying that a certain task is possible in one direction with side effects on mechanical means only, but it's impossible in the other direction, in the forward direction, in the backward direction, with the same mechanical means only. Constructor theory helps us defining mechanical means in a general way. So it really connects this notion, which was previously ad hoc and macroscopic, defining it, it helps us defining it in a general way, scale independently and independent of specific dynamics. And this is the notion of work media. So work media are the way I call the generalization of mechanical means. So these are objects that can, so in classical thermodynamics terms, we would call them, we would describe them as objects that can perform useful work on other objects, and they never dissipate. So they are just like, for example, a perfect spring that when it's compressed, it doesn't heat up, and then it can be decompressed again, and so on and so forth. A flywheel is another example. An atom prepared in a sharp energy state that can be excited or de-excited without dissipating. So it's an ideal kind of scenario here. We're considering a very ideal scenario, is another example. And they are characterized by, so you can define what they are instead of listing them in the way that I'm just doing here now to give you examples. You can ask yourself, what is it that makes all of these objects behave in largely the same way? So what is the feature that makes them all behave in this way, that they can be used in order to perform work or to store energy and then give energy without dissipating. And the answer to that is that they have in common some counterfactual properties, some properties that are about their ability or to perform a certain task. So the way we define work media is to give a set of tasks that are possible on them. And in this sense, work media are very similar to information media, which is some other class of media that I defined in a work with David Deutsch about information theory, where, for example, we defined all the objects that can contain information as objects that can have a set of states that can be permuted and copied. So it's all about the possibility or impossibility of tasks. That's one thing that we have to remember here. And the other thing is that this definition is very general because it's scale independent and doesn't require us to specify a particular dynamical law, which this is why it's cool. And for work media, we can do a similar thing. We can define this class of objects that have certain tasks being possible on them. And in this way, we provide a foundation for this idea of the second law being formulated in terms of the possibility of a task in one direction with side effects on mechanical means only, and at the same time, the impossibility of the reverse task with the same side effects. And so that's work media. Heat media are systems that have at least a couple of states, A and B, with the property that when you can go from, let's say, A to B by having a side effect on a work medium only. But if you try to now go from B to A, so to perform the task of going from B to A with side effects on work media only, then that's impossible. And so an example of a heat medium is just a volume of water with different temperatures available. So if this is in a way an obvious example and connects to what I already said before. So if you try to heat up this volume of water, you can do so by isolating this volume of water inside a container and then stirring very hard with like a stirrer, I don't know, a spoon or whatever. And this is a mechanical means being used in order to heat up the water. But now if you try to cool it, which is the reverse task, so go from a higher temperature to a lower temperature by using the same mechanical means, so by stirring, you will see that it's impossible. And this is something that was already well known in classical thermodynamics, but in constructor theory, we can now define heat media in this very general way as a generalization of these objects that have states that sometimes in thermodynamics are called thermal states. So states that when they are transformed into one another, necessarily produce some kind of dissipation. But instead of, so this is what I just said now is the language of the old thermodynamics, and I'm using it because I want to explain this in ways that can be reasonably understood by people who are not necessarily into constructor theory or other things. But the key difference in the constructor theory approach is that you can talk about this idea of dissipation and so on without using the usual approximations that thermodynamics does. And the key to all this is really this idea of work media, because the definition is very general, is scale independent, and it doesn't rely on a specific dynamical law, which makes the original axiomatic approach much more powerful and general than it would otherwise be.